In this video, we are going to learn about an important reaction that converts carboxylic acid groups into esters. This reaction, where we react a carboxylic acid group with an alcohol to yield an ester, is referred to as Fischer esterification. You may be sitting there asking yourself, why do we have a lipid profile matched up with the Fischer esterification discussion? The reason is that the Fischer esterification reaction is very, very linked to lipid chemistry. One example of how this reaction is linked to lipid chemistry is with the relationship between so-called fatty acids, which are carboxylic acid containing molecules, and triglycerides, shown here in this lipid profile. Triglycerides are molecules that contain three, hence the word tri, ester groups. And the way that triglycerides are assembled is that three fatty acids, which contain carboxylic acid groups, react to form molecules that have this three ester group called a triglyceride. So in this video, what we are going to focus on is the foundation of how we convert a carboxylic acid group into an ester group so that later on we can apply this knowledge toward understanding how lipids interconvert from one to the other, specifically looking at how fatty acids are converted into triglycerides and more. So let's go ahead and take a look at the general Fischer esterification reaction. The Fischer esterification reaction is a reaction that occurs under acidic conditions, where there's an acid as the catalyst to the reaction. And the overall reaction is that we start with a carboxylic acid, which I will abbreviate with R, representing the alkyl group that is bonded to the COOH group. And I'm going to show that bond to the OH group here explicitly because that's going to be an important bond as we look at what's happening in this reaction. In this reaction, we mix a carboxylic acid with an alcohol. I'm going to show the alcohol here in red, and I'm going to represent the R not just as R but as R prime to indicate that this group over here could be a carbon chain or ring that doesn't have to be identical to the one over here. These two groups could be identical, but they could also be different. So that's why I'm calling one of those R and one of them as R prime. This is an equilibrium reaction, and it takes place in the presence of acid. And the acid's function here is as a catalyst. A catalyst is a substance that dramatically speeds up the rate of reaction without itself being consumed during the reaction. So in other words, the catalyst that is present here would be at the same concentration at the beginning of the reaction as it is at the end of the reaction. It is simply there to speed up the rate of the reaction. It doesn't affect the outcome of the reaction, it affects only the rate of the reaction. So in this reaction, what will happen during the course of the reaction is that the structure O-alkyl that is bonded to the alcohol is going to replace the OH group of the carboxylic acid. So these two groups are going to switch during the course of this reaction. And therefore, the product of the reaction will be represented by having our R group of the carboxylic acid still bonded to the carbonyl, as we show it here on the product side. But now instead of having OH bonded there, instead we have OR prime from the carboxylic acid, from the alcohol. The other product of this reaction, since we are switching who's bonded to whom here, the OH group that we had in black from the carboxylic acid comes over here and is now bonded to the red hydrogen, making H2O as the other product of that reaction. So I'll show HO in black to match the hydroxy group of our carboxylic acid, and then I'll show the remaining hydrogen here in red, like so, to show our balanced chemical equation for this reaction. And the cool outcome here is that we have effectively taken a carboxylic acid plus an alcohol, and the product of that will be an ester plus water, where the ester is generally the product of interest. Hence, we call this an esterification reaction because we are creating an ester as the product. In the case of fatty acid metabolism, fatty acids are molecules that have long carbon chains here on the carboxylic acid, and we can react up to 3 of those with a single molecule that has 3 alcohol functional groups. And reacting with that molecule that has 3 alcohol functional groups, called glycerol, we generate a so-called triglyceride product, which has up to 3 ester groups, where we, in each case, have taken the alcohol, O-alkyl group, and replaced the hydroxy group of the carboxylic acid with that O-alkyl group from the alcohol. So let's apply what we have here at the top toward an actual example where we fill in some functional groups here. So we're going to indicate that we're going to be asked to provide the major organic product of the reaction of benzoic acid with 1-butanol, or butan-1-ol for short. And we're going to say that there is an acid catalyst present. So in order to predict the product of this reaction, what I would absolutely advise doing is drawing out the structures of each of these molecules to set up our reaction. For benzoic acid, we will have a COH group directly bonded to an aromatic ring. Don't forget to make that molecule aromatic. We have butan-1-ol, or 1-butanol, as we could also call it, and that's going to have a hydroxy group directly bonded to a 4-carbon chain like so. We have our acid catalyst present, which I'll just abbreviate as H+, which is a valid way to represent an acid catalyst because the acid catalyst is providing that source of protons. That is also going to keep the pH of the solution relatively low, meaning that this OH group would remain in place here in the carboxylic acid reactant rather than getting deprotonated due to the pH of the solution being relatively high. Instead, the pH of the solution is relatively low because we have that acid present there. So what's going to happen during the course of this reaction is we need to map out what the O-alkyl group is of the alcohol, because notice up here what happened was that the oxygen and whatever alkyl group was wanted to replaced the OH group of the carboxylic acid. So in this particular molecule, our alcohol, our oxygen starts here, and this would be our alkyl group here. So this particular group is what we would refer to in our generic example up top as the OR prime group. The OR prime group up here. It's the OR prime group because of the fact that it is the alcohol, and we're looking at the oxygen and whatever carbon chain or ring is bonded to it. So that takes us through right there. And then from our carboxylic acid, our OH functional group is right here. And so what's going to happen during the course of this reaction is that these two are going to switch positions. Now the mechanism for this reaction, that is the series of electron pushing arrows and steps to go from reactant to product, is a bit beyond the scope of this class, but if you take a full semester of organic chemistry, you would learn exactly how to go about transforming these reactants into the products, demonstrating that this isn't some sort of magic show here, that there is a logical flow of electrons that allows this process to take place. So now that we have done this, we should, as a way of checking our work here, show that we have started with a carboxylic acid reactant along with an alcohol, as are the prerequisites for a Fischer esterification, and that our product indeed has an ester functional group. If we are asked to predict the major organic product here, we don't have to put the water product in. The water product would be necessary if we were asked to provide all products, but usually we're just asked to provide the major organic product. And indeed, we have an ester group right through here, giving us some way of confirming that our structure is on the right track here. It at least has the right functional group. And to confirm that it's exactly right, we expect the O-alkyl group from the alcohol to be bonded where the OH group was of the carboxylic acid. So originally in the carboxylic acid, we had the OH group bonded to our benzoic acid. And in the product, now we have replaced this O-alkyl group from our alcohol, that was our 4-carbon chain with the oxygen, and that's gone here in place of where the OH group was in the starting material. So this completes our Fischer esterification product.